Quantum entanglement, the spooky connection across the universe. Imagine a connection so deep that two particles, even if separated by vast distances, can instantly influence each other. This phenomenon, called quantum entanglement, is one of the most mind boggling concepts in quantum physics. Today, we're going to unravel the mysteries of entanglement, explore its implications, and understand why Albert Einstein famously called it spooky action at a distance. What is quantum entanglement? Quantum entanglement occurs when two or more particles become linked in such a way that the state of one particle is directly related to the state of the other, regardless of the distance between them. When entangled, these particles share a quantum state, meaning their properties, such as spin, polarization, or momentum, are correlated. For example, if two particles are entangled and one is measured to have an upward spin, the other will instantly have a downward spin, even if it is light years away. This instantaneous connection defies the classical notion that information cannot travel faster than the speed of light. The science behind entanglement. The process of entanglement begins when particles interact in a way that their quantum states become intertwined. After this interaction, the particles can no longer be described individually. Instead, they are described as a single, unified quantum system. The mathematical framework of entanglement is rooted in the principles of quantum superposition and wave functions. In superposition, a particle exists in all possible states until measured. When entangled particles are measured, the superposition collapses and their correlated states are revealed. This collapse occurs instantaneously for both particles, no matter how far apart they are. How entanglement is created. Particles can become entangled in various ways, including collision or interaction. When particles interact, their quantum states can become correlated. Decay of a single particle. A particle splitting into two particles often results in entangled states. Engineered systems. Scientists create entangled particles in laboratories using lasers, specialized crystals, or other quantum systems. Einstein's skepticism and Bell's theorem. Albert Einstein, along with Boris Podolsky and Nathan Rosen, published the EPR paper in 1935, questioning whether quantum mechanics provided a complete description of reality. They argued that entanglement implied faster than light communication, which they believed was impossible. Einstein famously referred to this phenomenon as spooky action at a distance. In the 1960s, physicist John Bell formulated Bell's theorem, providing a way to test the validity of entanglement experimentally. Bell's work showed that the predictions of quantum mechanics could not be explained by any local hidden variables, the idea that particles have predetermined states before measurement. Experiments over the decades, including those by Alain Aspect in the 1980s, have confirmed the reality of entanglement, supporting quantum mechanics over classical explanations. Experimental proof of entanglement. Experimental verification of entanglement has been achieved through sophisticated setups. Key experiments include Aspect's experiment, 1982. Alain Aspect and his team demonstrated entanglement using photons and polarizers. Satellite-based tests. In recent years, scientists have entangled particles over distances exceeding 1,200 kilometers, using satellites to test the limits of quantum mechanics. Quantum random number generators. Modern experiments use entanglement to ensure that choices in experiments are unbiased and random. Applications of quantum entanglement. Quantum entanglement isn't just a theoretical curiosity. It has practical applications that are transforming science and technology. Here are a few key areas. Quantum computing. Entanglement is a cornerstone of quantum computing. It allows quantum bits, qubits, to process information in ways that classical bits cannot, enabling exponentially faster computations for certain problems. Quantum cryptography. Entanglement-based encryption methods promise unbreakable security. Any attempt to eavesdrop on a quantum communication link disturbs the entangled state, making eavesdropping detectable. Quantum teleportation. Scientists have used entanglement to teleport quantum states from one location to another. This isn't teleportation of matter, but rather the transfer of information about a particle's quantum state. Notable experiments have successfully demonstrated teleportation over several kilometers. Metrology and sensing. Entangled particles are used in precision measurements and sensors, enhancing accuracy beyond classical limits. Applications range from gravitational wave detection to medical imaging. Quantum networks. Efforts to build quantum internets rely heavily on entanglement to create secure, instantaneous communication across global networks. Philosophical and scientific implications. Quantum entanglement challenges our classical understanding of reality. It suggests that the universe is fundamentally interconnected in ways that defy our everyday intuition. The non-local nature of entanglement raises profound questions about the nature of space, time, and causality. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that entanglement reflects the branching of parallel universes. Others, like the Copenhagen interpretation, emphasize the role of the observer in collapsing quantum states. These debates highlight the deep philosophical implications of quantum entanglement. Beyond physics, entanglement in nature. Recent research suggests that quantum entanglement may play a role in biological processes. For example, photosynthesis. Quantum coherence and entanglement might explain the high efficiency of energy transfer in plants. Bird navigation. Some studies suggest that entangled particles in birds' eyes help them sense Earth's magnetic field. These discoveries hint at entanglement's relevance beyond physics, potentially impacting fields like biology and chemistry. The future of entanglement research. As experimental techniques advance, scientists are exploring new frontiers of entanglement. Large-scale entanglement networks, or quantum internets, could revolutionize communication and computing. Researchers are also investigating the role of entanglement in biological processes and the fabric of space-time itself. Recent experiments have even tested entanglement over record-breaking distances, including satellite-based experiments that entangle particles across Earth's orbit. These developments hint at the possibility of integrating quantum technologies into everyday life. Conclusion. Quantum entanglement is a testament to the strange and beautiful nature of our universe. It connects particles across vast distances and challenges our understanding of reality, space, and time. From quantum computing to cryptography, entanglement is at the heart of groundbreaking technologies that are shaping the future. If you've enjoyed this journey into the quantum realm, don't forget to like, comment, and subscribe to our channel. Let's continue exploring the mysteries of the universe together.